Let's take a look at RGB Color layer basics in ProRaster. I'm using ProRaster Premium. This video builds on the image layer basics video, and if you haven't already watched that, you should do so first. So an image layer acquires color directly from a single color band which contains red, green, blue or red, green, blue alpha and displays that color without modulation. The red, green, blue layer does the same, but it's more manual. So you have to connect the red, green and blue color components to separate data bands and then you have the option to modify the data map for those bands to change the color mapping. So in an RGB color layer, we have red, green and blue components, and then we have the intensity, which is the hill shading, and the opacity component, which is for per pixel transparency modulation. So to get started, you'd go to the red component and connect to a raster source. So I'm going to connect to an old color photo. So in this case, I've just browsed straight to the raster. I haven't had a raster source already prepared. Now, it's not doing things automatically for me, so I have to set things up myself. So I have to choose the band for each of the red, green and blue components. So red is okay, green needs to go to the green band, and blue needs to go to the blue band. And so there I have my color photo. So for each of your red, green and blue components, you have to choose you have to specify a mapping from data, which will probably be some kind of integer values from 0 to 255, through to color. And each of these will look up a color table. So here for the red component we have a red color table, for green we have green, for blue we have blue. These are fixed, you can't edit them. If you try and edit them, it just gives you this message. But you can still choose your own transformation. So you might use, for example, no transform and probably pass index. So in this case, we've got red, green and blue data that's just integers, so we can go pass index on all three of those. So we're passing through the color index straight through, that's mapped through the color table. So effectively what we've got there is no color stretch of any kind, that's just unenhanced. Another way that you can treat your color is use a color transform and then specify the number of bits in your color data, and 8 of course corresponds to 256 colors, which is the same number of color bits in our color table. So if we go through and set the color transform for each one of our bands to 8 bits, then again we get no stretching whatsoever. So that's also quite a useful one. You can do a linear transform. Now this is based on the statistics, so at the moment it's on linear transform and it's just pure linear. So it's going to map between the minimum and maximum values in the raster itself. Now that might not be from 0 to 255, so it might be somewhat less than that. So and then that data range is then mapped out to 0 to 255 in the color table. So by going to a linear transform, we'll see a little bit of color stretch. It might not be very obvious in this particular raster. If we go to something like an equal area transform, then we'll see far more obvious color stretch. So now we've got a quite obviously different color stretch. Another one that's quite useful is the sigmoid transform. So you can use sigmoid lightening and sigmoid darkening. So I'm going to go for sigmoid lightening on all three. And with a value of 25, that's just given me a little bit of lightening in this image. So sigmoid transform is sort of a curve between the minimum and maximum values, and and you can bring the curve up or down to lighten and darken across the range. If you wanted to use a linear transform, but you didn't want any enhancement, then you can use linear with a manual clip, and then put in 0 to 255, which represents your color data. So now we've got a linear transform between 0 and 255, mapping to our color table, which is between 0 and 255. So in this particular channel, in the blue component, we now have no enhancement of color. So let's try another color table. So let's have a new RGB algorithm. Let's have a look at another bit of aerial photography. So this is a JPEG 2000 file. So we need to connect it to the red, green and blue bands. And if we have no transform pass index, then that's the unenhanced color. And you can see that it's sort of quite blue. And so we can go into the red, for example, and put in a little bit of sigmoid lightening. And as I bring that up, you'll see that it gets progressively more red. And then perhaps go into the blue. Perhaps use a sigmoid darkening transform. Something like that. Oh, maybe 25. So now I've done some enhancement on both the red and the blue components, and got something that looks a little bit more realistic. It's more green than the original aerial photograph. The main application of this kind of layer, red, green, blue layer, is probably for, in addition to aerial photography, also for multispectral satellite. So I won't give an example of that today, that's a whole other subject. But of course, if you've got Landsat data or Sentinel data or Spot data or whatever you have, you connect your red, green and blue components into different band combinations for those satellite scenes, and can produce different visualizations of that multispectral data. So that's probably the major application of this layer. Another application is scientific data. So for example, let's browse to another raster. I've got some radiometrics here. This is Australian radiometrics. So radiometrics is often presented in a potassium, thorium, uranium, red, green, blue scheme. So let's choose potassium, thorium, and uranium. And then probably go into the stretch and give it a equal area transform stretch perhaps. And that's kind of visualization that people use for radiometric data. Then go looking for uranium deposits and various things like that used in mapping and mineral exploration. So just having a look at some of the layer properties. So all the same as imagery, you've got your coordinate system there, you've got your valid cell by component rule. We'll look at that another day. On the color page, You still have your grayscale option. You can balance your color and intensity. So if we turn on intensity here, choose some DEM, and now we have radiometrics draped onto our DEM. Of course, we have our opacity modulation. I won't show that here. This gives us our color and hill shading balance as before, your opacity for blending, and of course you've got your color interpolation options at the layer level, and they're also available down here on the component level. And then there are some more advanced options. So reversing the color table, clipping beyond limits. These are probably things that you won't use in the red, green, blue layer. They're for the lookup table color layer. And then transform raster source. So again, this is, well, it might be something that you'd use with satellite multispectral data. So in this scenario, you're creating a data transform from statistics, but you're using the statistics of some other raster. And that can be used so that you have, say, multiple scenes all matching the statistical transform of some other raster. So that can be useful in that scenario.